Okay, I think we can start. I see all of the teams are around, at least one student per team. That's good. So yes, we start our session today with your presentations from all the work you've done in these last 2 days. So we look forward to see your updates and see how you improved your presentations based on our feedback. So let's start with GrowbotHub. Go ahead, Aurelien.
Hi everyone, I'm Aurelien, the team leader of GrowbotHub. We aim to grow and harvest vegetable in an autonomous way. Sorry for that. This is the leading team, technical team. Myself and Philippe are doing system engineering. Amélie is doing mechanical design. Justine is doing chemical engineering. Jonas is doing robotics, and Rosando is doing all the aeroponic systems. Just a little overview of the organization. We have the technical board and the operational board with communication, finance, and sponsorship. A little bit of history of GrowbotHub. We started with IGLUNA 2019 with our first prototype, the carousel. Then we moved to IGLUNA 2020, where we developed our own aeroponic modules. And this year, we're going to rebuild the structure from scratch and work on an interesting new project, which is robotic pollination, as we don't have bees on the moon. Our main objectives, optimize space with our new structure. Another objective is work through the whole plant life cycle. As I said earlier, we want to pollinize plants to produce seeds to be able to reseed new vegetables every time. We want to produce vegetables that are suitable for human consumption, and we really want to have a sustainable thinking when designing the whole project. This is a bit of an overview of the new project. I don't have an image as we are redesigning the entire structure this year, and we'll start next week, but we'll have a modular approach with aeroponic modules inside a modular structure with different modules that we will develop separately and combine together. So we'll have the robotic part, which is doing the harvesting, moving plants, pollination. We'll have the control part with plant monitoring using computer vision and the scheduling to be able to produce vegetables continuously. And finally, some chemical tests and quality controls that we're doing separately. Now I'm going to talk about the major risk. I'll just go through one major risk by subsystem. In general, we need a really good understanding for compatibility between the different modules to be able to put them together nicely. With the structure, as we're building an automated structure, we need to improve the reliability of the automated parts. For the computer vision, lack of data sets, we had the same problem last year. Robotics, we need compatibility between the different suppliers. We already had this problem last year. Supervision, last year we have a top level controller, one single point of failure. This is a big risk for the project and a health risk linked to aeroponics. So as I said, we want to build a new structure to save space, and we want to test that during the field campaign. The structure needs to be autonomous, using human urine for aeroponics, and protect the environments. Last thing, the partnership with the different teams. We want to share knowledge with P04, design our structure to fit into the habitats, and optimize our consumption. Thanks for your attention.
So I am Riccardo Stivalessi from the team Loops M from Italy. And we were last year the project VGEM that had various objectives. Mainly, we wanted to focus on our cultivation system that we wanted to test on Mount Pilatus. But we also wanted to design a lunar greenhouse to put our virtual environment in. as we had to recreate all the activities of the Horde Cube, our cultivation system, in a virtual reality environment for a virtual reality experience. Since this year, we have a very big team, as we have 19 people working on this project. We wanted to enhance each aspect of the project. So we wanted to enhance our cultivation system with a new bioconversion system and automation system, but we also wanted to enhance the design with a new micrometeoroid shield. And we wanted to enhance also the virtual reality experience, all going towards a lunar operative outpost for the production and storage of microgreens. For the bioconversion system, our goal is to add a waste recovery system based on insects, and its main challenge will be the control and management of the growth process. We have also an automation system which has a goal to grow microgreens autonomously from sowing to harvest, and its main challenges will be to assemble the robotic system and the software development. We also have a micrometeoroid shield for the design, and we want to design a specific prototype shield for the protection of the lunar greenhouse. And its main challenges will be the complex testing environment required and the sourcing and selecting of prototype materials. While last but not least, we want to enhance the virtual reality, upgrading the VR experience. Although we only have 2 people that can actively work on it so far, so its main challenge will be the time commitment. To the field campaign, we want to bring the cultivation system with the new bioconversion system and automation system fully integrated, but we also want to bring the prototype, hopefully tested, of the micrometeoroid shield. And last but not least, again, the virtual reality experience. We did a very detailed risk analysis, although we put here only the main risks that we think that we will have to face during this year. And probably the main ones will be the development of the robotic arm software due to the lack of knowledge and experience, and the limited access to the railgun laboratory for the testing of the micrometeoroid shield. We have already thought of a few mitigation actions already for all of these risks. So hopefully the final outcome will be as expected. And we had a few meetings with other teams during these few days. And for example, we talked with P5, and we talked about the possibility to test a substrate that they could make if they find the possibility and they managed to actually create it during this time. So we could test it out and see if it works for an actual cultivation system. But we also talked with P6 Habitat about the possibility to bring our experiment inside their tent. At the moment, it's not feasible because there's not enough space, but we have sponsor, Plasteco Milano, that has already provided for us a tent. So we know that they have the expertise that Habitat may need this year to build a bigger prototype. So we'll try to connect with Plasteco Milano to provide some expertise to Habitat and see if we can later then fit in their tent, in their prototype, sorry. So also we had a light social talk with the Project 8 Light, in which we shared our experience and expertise, and we talked about our differences and our similarities, as we use different prototypes. We use the Oculus Quest, for example, while they use the Oculus Lens. But we both use Blender for our models, although, again, we use the Unreal Engine to power the Oculus Quest while they use Unity so far. And that's about it. Thank you for your attention.
Yeah, well, hello, everybody. Good afternoon to most of you. My name is Adrian Ricardes, and with my partner, Milinjani, we're going to present today, again, the Lunar Ice Extraction and Electrolysis project. So as you remember, the mission statement is based on the demonstration of the use of semi-autonomous rovers to extract the water ice from the surface of the moon and decompose it into its constituents, hydrogen and oxygen, using the process of electrolysis. So these are the main objectives that we want to demonstrate, that we actually want to test during the field campaign, to design and to develop a mechanism for extraction and also for collection, to develop a semi to full autonomous system operation, and finally to develop a system to process the collected ice into its elements. So this is mainly the project concept. I am going to omit right now some previously discussed detailed points. So the Pilatus comlink mainly communicates the control room, TTNC, and the communication module that is on the rover. This extraction rover processes this internally in order to deploy the extraction mechanism to collect this ice raw material, to store it into the storage unit, and finally bring it back to the storage hub so that it can have an electrolysis process. So, well, what have we done until now? Several people from my team have already started in parallel doing some research in several subsystems, such as the OBC and EPNC, TNC, and the budgets and the risks, of course. But basically, we have two categories, the mechanical method and the passive heating method. In the mechanical method, we make use drills, cutters. It depends, something like a CNC machine. And the passive heating method may have an array of lenses in order to direct this solar radiation, this sunlight, to hit a focusing point, a point of interest on the surface, and to collect this ice. So this has to be analyzed with a trade-off, multiple trade-off tables, but yeah, we have already started with this. So Milind, could you please go with the presentation? Thanks.
Okay, yeah, thank you so much, Adrian. So as my partner Adrian already discussed, that we are in the analysis phase for analyzing what exactly the tools we are going to use for extraction. So there are some risks which are irrespective of what methods that we are going to use for extraction of the water ice. So they are as follows. So one is the power failures, that is the most critical risk. The structure stability and stiffness is also one of the top level risk, and the uncertain environmental conditions, which is also one of the risk while demonstrating the project in the field campaign. So these are the top level risk, and once we have some detailed analysis about our project, then we will be able to gain some more insight about the risk. So yesterday we had some discussion with other teams. I won't go into detail about what we discussed, but just an outcome of what has been discussed with the other teams. So we discussed about our project ideas, and also try to identify some similarities in the concept from the technological perspective and also demonstration perspective. And we have agreed in this fact that once our system and our basic we are done with our analysis phase, we will be again meeting with all these teams in order to see if we will be able to collaborate in future or not. But I'm being optimistic that yeah, we will be able to collaborate in the near future. So this was regarding discussion with the team and what we'll be bringing to FC, our field campaign. So as we are developing rover, so we'll be bringing the rover platform, the scientific payloads that we want to test, which is our extraction and electrolysis tool, spare parts and spare batteries which are necessary for operating the other subsystems, and lastly, exhibition materials, for example, brochures, posters, and some other relevant media aspects which will be helpful in exhibition during our exhibition. So this was regarding what we will be bringing to FC. And this we had already discussed in our previous presentation as well, our team structure with our 3 of our academic supervisor, and we are a team of 10 people who are working on this project. So yeah, thank you so much for your attention, and yeah, you can contact us on these channels.
Okay, so hi, my name is Caroline, and I'm from the project sample 2. Here is our team structure. So today they are with me Ryszard Zabiła and Gabriela Myskowska and Patrick Sulej. While working on our project, we are divided into two departments, the biology department and the engineering department. And our biological group focus on research of bacteria and plants, while our engineering group concentrate on mechanical as well as electronic and software aspects of the project. So our project is an extension of the sample project with aims to create a lab supporting system of modules located outside the main habitat. We have a basic idea. In a box, we put soil, seeds, and water, and we provide the right environment for growing plants using proper lamps and controlling the temperature. After time, the plants grow and we will be able to collect samples. The twist is the soil we want to use because we are going to mix lunar soil equivalent with bacteria such as Geobacteria and Chavanella and human feces in order to create environment for effective plant growth. Using those bacterial species will improve soil properties and plant growth because they have the ability to oxidize organic compounds and metals to non-toxic carbon dioxide.
Up to this point, we have built an inner structure and mounted labs inside, but we still need to wrap the whole thing with isolation and finish the electronics. The next step will be dealing with the problems that the previous team have encountered, such as overheating of the module and power supply issues. And to overcome them, we are in the middle of the process of designing a cooling system and calculating heat exchange. And once we have everything done, we can determine whether we need any extra power supply or not.
During the field campaign, our main goal would be to grow plants on terraformed soil and check if bacterial terraforming is a valid solution. Also, we would like to look forward and check if any of the ideas discussed with other teams work out in the field. And that entails certain risks that meet others, for instance, plants not growing because of various reasons, such as damaged or malfunctioning seeds, or that the soil won't be contaminated, or that the soil will be contaminated, or it won't be fertile enough to actually be able for us to grow anything on it due to the wrong mix.
We have talked to 4 teams and we were able to find 2 immediate collaborations. A team P12 PowerHab 2 could be our power supply, and that will hopefully solve a lot of problems for us. And we want to schedule some training session with P01 to exchange knowledge regarding plant growth. And also we find a few possible collaborations on our development path. A team P03 could be our source of water, P11 could collect lunar soil for us, and P01 could harvest grown plants, and this would allow to remove human factor and fully automate our project, which would be great. And yeah, we were very happy to talk to everyone and discuss our project and find connections between them. Really look forward to seeing you soon, and hopefully we can meet in person one day. And thank you for your attention.
My name is Juan Carlos. I'm the team lead from XT Space. We were part of the IGLUNA 2020 as Ampex. We were, as you can see here in the team, you will see some known faces. We are still in the process of getting building a team, but so far we have already 9 people that are going to be part of us, part of the team, and they are really motivated for it. Some new faces that will come soon. So as maybe you know already our project from last year, our motivation is to produce fibers in in situ on the moon out of the moon material. This is a in situ resource utilization technology, and the fibers that could be produced on the moon could be used for many applications. It's up to the scientifics. But we have here some possibilities like fiber reinforced composites that will be important for the infrastructures, filters and thermal insulation that will to make possible the habitat. And then we have, for example, for hydroponics substrate that will make possible to grow plants without the need of having the usual soil. Our mission, of course, is to produce this machine that will make possible the production of fibers out of moon regolith. For that, we're aiming to have a small and simple and robust machine, just in case that if it needs any kind of maintenance, the people that like the astronauts could have it easily and understandably. So for this year, we're aiming to go a little bit farther. In comparison with IGLUNA 2020, this time we will bring as a miniaturized machine, as I said, but the environment that we're aiming for is vacuum after the recommendation of Jan Werner, the General Director of the ESA. And then we have the possibility to fly the machine on a parabolic flight, thanks to Deutsche Luftfahrtraumfahrt. But this part of the requirements for system still need to be discussed. We're still, as I said, we are building the team and doing brainstorming. So it's not yet for sure how are going to be the requirements. We want to be realistic. For that reason, we don't know if we are going to have the time in just 1 year to make possible a parabolic flight certified machine. And then for potential collaborations, we have the opportunity to speak with P2 Loops and P11 Rebels. And I think that there is some potential collaboration with them. They are really nice people, and they're looking for Loops M, they are looking for having some fibers that they could use as a substrate. And for Rebels, they would like to have some of the material that we will use for experiments, for their tests. This is something that we still need to concretize with the responsible of this, that will be our university. But I think that it will have a good future, these collaborations. As explained before, like our potential risk are students because of examination period that we are going through right now. Many students are unavailable, so we are still working on that. I think that it won't be any trouble. Then we are afraid that there will be not enough money for the building because of COVID-19 outbreak. There has been less cooperation from some of the companies that we were in contact. We're still working on that. I think that when we have a build team, there will be more clarification on that topic. And then about the time, that's an important part. Like the time lap of IGLUNA 2021 is pretty small. So it has some coincidence with our timeline in the university for examination. So it's something that we have to take into account, and for sure we will do. And so far we have some interested partners. We still have to concretize and make it official, but some of the last year partners like Maxon and Airbus are interested on keeping the cooperation. Some new companies, Wilbur, Trumpf has shown quite a lot of interest on working with us. And then we have Saxonia and Cobes. They will be for sure with us. And Black Wave, it's in relation with Airbus, and I think that we will have any trouble having them. Plans for the Hans Hermann Voss Foundation, they are our main economical or financial support. We hope that we will receive it this year too. So that's so far. Thank you very much for your attention.
Hello, I'm Lubov, and together with my team, want to present you our project P6 Inflatable Lunar Habitat. This is our team. For now, we have two supervising professors for architecture and construction, but we are in a search from two others from civil engineering and mechanical engineering. We are three architecture students, but we search of other team members for engineering, building physics, and building technology, and IT engineers. Our main concept is to build a module that have inflatable, flexible lie-down structure with a visible inflatable support structure and offer space for scientific experiments, and is separated by airlock. This module should be flexible with light condition modes 30% transparency, stable against mechanical impacts, and not at least with right regulation, climate regulation. Until this year, we make design of our project or of our habitat and data drawings of the details, but we are now only of the theoretical level.
For this year, we would like to concentrate on bringing the habitat to life, and we are going to work on developing the following subsystems by finding the right materials and experiment with them. The goal is to create a construction stable enough to resist the extreme condition on Mount Pilatus. And these are the subsystems seen on the graphic that we would require from the infrastructure: only a Wi-Fi connection for the sensors, for temperature, pressure, and the cameras we would like to have inside the habitat. And we would also need the electricity for a pump and the air condition, since those are not our main focus, and therefore we are not, we don't have a self-sufficient systems for now. Apart from that, we would like to do the following contribution to the educational exhibition in the museum, where there would be a video with showing how the construction is it's happening, and maybe as of the suggestions from today, we could also integrate a simulation of bad weather condition and the reaction of the structure. We could also bring a model and a poster explaining all of the details about it.
Okay, so for the next step, we will need to look for more sponsorship. So if we got enough sponsorship, we will be able to build out for the test bed. However, if we don't, we will need to be simplify the model for one-to-one scale, and it will only for the exhibition. And this will be some of the potential industrial and also academic sponsor we are looking for. So this will be the backup plan, as we will have one-to-one simplified model and place it on the exhibition. And for the risk analysis, we will, for now, the main issue is like the sponsoring, financial, and then after that will be human resource, materiality, construction, building, and internal condition, testing, prototype, and logistics. This all will be all time, and after that we will have this for the during the field campaign. We will need to concern about windstorm, fire, electricity, and also insulation. And now is a future step. After reaching out the sponsorship and making the decision, we will then need to focus on testing materials, finding the right materials, and building it up to 1 to 10 model in order to create an analysis extreme conditions. Yeah.
We had a couple of very nice talks with the other teams. And for now, GrowbotHubs and LoopSam would like to have the space inside the habitat for putting their experiments, which sounds great because this is both helping for our teams and for theirs. LUIEE would like to exchange some knowledge about the dome construction, and we are very happy to help if we can. The rebels would try to build a protective shield around our habitat if it goes to this scenario. These are all things that we have to communicate again in time. And Ray could also make the lighting installations and make an experiment with the interior atmosphere when the habitat is placed on the exhibition. So we are still unsure of which one of those will work, and we are looking forward to see the next steps of all of the experiments and see what could work together well. Thank you.
Thank you.
So I'm going to give you a brief overview of our new presentation for the kickoff event. So we are, as always, 7 students from ESA Supero plus our supervisor, Professor Stéphanie Levy-Destret. And now we are looking for people to help us in the outreach and communication part, in the sponsoring, with the exhibition setup, plus 2 other people on the operation and SLAM algorithms for our field campaign. So we will have enough people and enough resources to be successful for the campaign. So our partners are still CNES, Sonera, of course our university with the different departments of aerospace, autonomous navigation, and hardware setup, the Swiss Space Center, and Airbus. We want to test autonomous operation and autonomous navigation on collaborative robotic systems. So our main objectives are to perform outdoor navigation and plan and move towards some targets that we have seen during the autonomous outdoor navigation. We are going to bring with us a rover and a drone, probably more than a rover and a drone, just to have some backup plans. And we already have here in our universities different rover platforms, different drones platforms. We have still to decide which one we are going to bring to the campaign. This will depend on the insurance that we have to pay to move and to operate the drones, as well as the environmental campaign setup. So if there is too much wind, we probably are going to use a bigger drone, and we have to do some tests here to understand which is the platform that is more suitable for the campaign. We already have some algorithms for autonomous operations and task planning, as well as some indoor SLAM algorithms for the rovers. So what we want to test during the campaign, we want to test outdoor navigation algorithm, the task planning algorithms, and the path planning algorithms on both the rover and the drone. What we need from the Swiss Space Center, of course, we need an open field and technical support and help to set up our the campaign and be successful during the IGLUNA field campaign. And we hope to be able to move in a known environment, avoid obstacles, and map the surroundings, and do some operations in the field. We are going to bring with us our drones and rovers, as well as our PC with the ROS setup. Of course, the humans that has to be always on the field looking at the drone for certification requirement and flying drone in Switzerland, as well as some backup material for maintenance in case we have some kind of failure on the drones or the rovers. So from the difficulties of the last presentation, we derived a bit of mitigation actions. There was more a brainstorming part. So if there is too windy, we can use 2 rovers instead of the drone of the rover to perform SLAM. If the wind is not too much, we can even change drone platform because we have different platforms for drones. For the temperature, we can preheat the batteries in order to have enough autonomy for our operation, as well as putting the batteries near the GPU or CPU so they can be warm. If there is slippage, we can or replay the mission with the drone or test integrated performances. And if for the camera, we're going to test the camera in different lighting conditions here at ESA and with our partners. If not, we can always rely on the other sensor for our autonomous navigation. For the communication constraints, we are again going to test everything here before going to the field campaign, and we hope, of course, to be able to test during February at the midterm event. For the global map, if we don't have a global map, we can always use local path planner and proactive planning. For localization, we can always try to relocalize from some landmarks that we are going to set up on our field of test. Or we can always evaluate some performances in a non-ideal situation, in a continuous situation. There are always valuable data. And for the onboard computer data management, we are going to test everything here, of course, before going to the field campaign. So the high-level planning that we have envisioned is that we are going to define which hardware we are going to use by the end of September, so we can start as soon as possible the test here at the ESA Lab laboratories. We are quite lucky because we can use the laboratories even if the situation with COVID is not yet stable. Then, of course, we have to think about the IGLUNA test plan for the field campaign. While we are doing some testings, we have the opportunity to do outdoor tests at CNES at the Air Mars terrain. So we're going to use this possibility, as well as test the drone with the ONERA. And then at the end, there will be the IGLUNA test campaign. We have talked with the P03, P08, and P010, or better P10. And that was very nice to meet them and talk with them. And we are going probably to collaborate on the part of autonomous navigation, path planning algorithms, and task planning and collaboration between the drone and the rover. And they will be very helpful for us to get some feedback from the other teams and understand their difficulties and find a way to be all successful for the field campaign. And that's it. Thank you for your attention.
So our project is LIGHT, Lunar Navigation Helmet version 2. First of all, I want to mention that this is a continuation project from last year's LIGHT, and our team lineup has changed. So we face some difficulties in mainly in coordination, and we have some management issues. But we talked with our coach, and we got useful feedback from several teams. So first of all, our team. I'm Chris, and together with Nikitas, we developed the software for our project. Lydia, Katerina, and Athena are on the graphics design team. And lastly, Panagiotta, Iota, and Kostadina occupy the electronics team. So we are, because of the limited time frame we had, we are forced to mention some features to repeat ourselves again. So our mission, LIGHT is a gadget-based technology which will provide navigation and assistance on lunar missions. So we talked with our coach, and she advised us to add some features in order to differentiate to last year's project. We thought about utilizing object detection tools, for example, OpenCV, or if we are able to, actually, if we are able to afford HoloLens 2, it will be better for us in order to implement more features. Also storing geolocation and providing features, for example, guidance to specific saved objects to the headset would be useful. And we'll have multiple use cases also in other applications, for example. And similar to last year, the user will have to fix some mechanics and check some devices. And the navigation this year will be smarter. In regards to, I mean that the path will not be predefined. It will be a smart navigation. So, and also this will be taking part in the exhibition area. In the test bed, we will have set up a weather box, which will provide and transmit environmental data through the HoloLens to the user. So some results we're expecting to have. We want the user to experience an analog space mission, and we want the data to be projected to the user through the repair map, and also add some repair mechanics, as I mentioned before. And we want to track objects also. So
also, before we go to the risks, I would like to sum up what we've already said.
And the main thing that we discussed with our coach is that you would like to see some intense differences with the lighter version of the previous version of the light project. The thing that we want to be working this year more severely is that we want to have smarter, that we want to make the whole experiment smarter, the whole project smarter. Last year, the students that were working on the project didn't have enough time due to COVID-19 circumstances and did a predefined thing. The task was predefined, the route was predefined. This year, we want to make it smarter, we want to make it flexible, and we want to make it more convenient to work to. And let's go to the risks.
Okay, as far as the risks are for this project are concerned, and we will also take some mitigation actions to resolve these issues. Some risks are limited funding, the potential delay or damage through the shipping. Some technical issues may also occur on the event, and we face some team management issues. And the mitigation actions are that we have to early start finding sponsors and keep track of our budget. We also have to improve our teamwork skills, and we will prepare everything for shipping to be on time, actually.
The way that we're gonna be presenting our project, there is gonna be the weather box that is gonna be sending information to the helmet, the HoloLens, and the way that we want to showcase it is that we will need a space. We've talked with our coach approximately 6 by 6 meters, and we're gonna have a whole installation there that it's gonna resemble the lunar surface, and the visitor, along with the helmet and the HoloLens glasses, will be able to have this experience of how it is to navigate the space and perform some tasks. And then we're gonna need.
Okay, but
you have already over 6 minutes, so if you could wrap up the conclusion of your presentation.
Okay. We saw that this we have a startup potential in our project because our project is multi-use case, as we mentioned last time. This is applicable in a variety of industries, for example, the medical construction industry. And this is a quick overview of what we are planning to do, and we may also improve some features and some mechanics.
This is a screenshot from last year's project.
Yes.
Thank you.
So thank you.
Okay, hi, I'm Jillian. I'm from the Lunar Zebro project, number 9. And Lunar Zebro is a TU Delft project consisting of students, but also staff members, in which we build rovers. This is our IGLUNA team. So Lunar Zebro actually consists of a much larger team, but we have a special group just for IGLUNA, and we're about 22 members. So as you can see, the slide is pretty full. So it was difficult to include names and positions, but we're divided into a group just for the rover, a group for swarming, a systems engineering group, a PR group, and also a management group to make sure that everything goes according to plan. And a bit more about Lunar Zebro as a whole. Our heritage is that the Lunar Zebro, or the Zebro concept, was brought to TU Delft in 2013. And we began with the space grade version in 2017. So what Zebro is, it's actually the Dutch short form for zesbenig robot, so 6-legged robot, and that's what makes our design special, is the C-shaped legs, which we have 6 of, and that's what distinguishes us from any other rover out there. And this is technology that we got from Rex, which is from a university in the United States. And the C-shaped legs are special because they allow us to walk over obstacles that we might encounter, like small rocks. And they also allow us to execute different walking algorithms. So we can walk normally, but we could also, for example, crawl or hop or employ a different algorithm for, let's say, going up a slope. And yeah, that's what distinguishes us from different rovers. So like I said, we're a big team and we have different projects running in parallel. We're working on our qualification model, but also on a precursor mission called LEAP, and also on several other analog missions. We've been on a few before to Hawaii, and IGLUNA will be another one of our analog missions, as well as probably another one in Iceland next year. And our main objectives for the IGLUNA field campaign are to validate certain elements of our design and also to demonstrate swarming. Our qualification model is being tested for the moon, but we are aiming to send just one in a couple of years, but our eventual goal is to have a swarm on the moon as well. So IGLUNA is the perfect platform for us to test this swarm. So yeah, these are our main objectives: the verification of the thermal design, testing out our communication, or sorry, our command and data handling system, our obstacle detection algorithms, and employing that for the swarming, and then also testing out our ground station operations and getting a bit more familiar with how that works. And like I mentioned, we've been to Hawaii before, and we did a remote ground station here in Delft, and that way we were able to connect with the team in Hawaii, and we were able to get visuals from our own rover and also the controls from our own rover, and we did some cooperative swarming with other rovers there, so from their cameras we were able to see our rover from a different angle as well. And that brings me to the collaborations. We've also spoken to teams P8 and P10. For P8, they're working on the HoloLens with the path planning for the astronauts, and they'll be building maps, and so will we. So we came up with the idea to cross-check our mapping platforms to kind of validate them against each other. And they'll be using weather stations, as you just heard, and that can also help us when we're mapping, and we'll use those as waypoints. For P10, we can do something similar as in Hawaii. We can do cooperative swarming with their rovers. So our aim is to have 6 rovers, but we can also have a few extra and then also employ their swarming algorithm on our platform, since our rovers are designed to be a platform to house different algorithms, but also different payloads. So we'll be testing the agility of our rover with another group. That brings me to our main requirements. I'll just read them quickly. Our mission will demonstrate the swarming technology with 6 or more Zebro rovers, like I just said. We'll be developing our own in-house swarming algorithm, and like I just said, we can also accommodate other swarming algorithms. We'll further develop our obstacle detection system to an obstacle avoidance system, and that way be autonomously navigating. And like I showed in the image, we'll provide more hands-on experience for our ground station operations. And we'll also be able to accommodate other foreign payloads. So if any other teams are also interested and we haven't spoken yet, we're still open to that. And now I'd like to hand the word to my colleague, Alex, to talk about our preliminary risk assessment.
Thank you, Gillian. With the preliminary risk assessment, we have a few main risks, including software fault, loss of vision, loss of connection, sensors which are not working, the lack of communication within the team, members dropping out, and a lack of sponsorship. With the risks from it, what will be on the field campaign, that these risks we can only grade as we have defined the boundaries of our vehicle. That's it, and thank you very much for your time, and please contact us if you have any questions.
P10, we are MISTLab, and we want to do multi-robot exploration. We're originally from Polytechnic Montreal, and MIST stands for Making Innovative Space Technologies. Together with our sponsor, Basler, who is providing some cameras for us, we want to take on this challenge. The team consists out of mainly PhD students from various backgrounds.
We have backgrounds in computer vision, computer engineering, electrical engineering, mechatronics, or embedded systems. And our supervising professor is Professor Giovanni Beltran. Our objectives for the multi-robot exploration missions are to set up a functional rover fleet for field tests based on commercial rovers. We want to integrate all of our different PhD projects for which we have developed technologies that I'm going to introduce in a split second, which have various TRL levels already. And as a third objective, we want to evaluate the integrated system on the analog terrain provided by IGLUNA. Yeah, I already mentioned we're all PhD students and want to make use of this opportunity for our dissertations. And we are motivated by space exploration in general. So what we want to do or envision is like a mission on the moon, not necessarily with these rovers, but when identifying interesting areas of interest on a planetary body, we want to go and explore them semi-autonomously and with the aid of our robot teams. And for that, we have, for instance, our simultaneous localization and mapping algorithms. Then we have self-healing and robust networking capabilities and different control modalities for remote operators that can be in the base. For the communications part, we plan to use 900 megahertz antenna, if that's possible. If not, we can switch to a second backup frequency there. Then this was technology readiness level 5 currently. It has been previously tested. For connectivity maintenance, we want to deploy our self-healing and robust algorithms, TRL3. Then we have UW ranging capabilities for the localization, TRL4, robust visual-based localization, TRL3, and then we want to test our intuitive control, which is currently TRL4, and we want to extend it even further. What do we want to do during the field campaign? We bring 3 rovers. It's currently in the making which robotic platforms we finally choose. It's going to be either Rover Robotics, which are on the right-hand side, or ClearPath Chacal, plus 1 RoboDog from Unitree. Then we get the time-of-flight cameras from our sponsor. In addition, we will deploy LiDAR sensors and RealSense 3D cameras to also compare the different sensors to the BASLA camera. That's what our sponsor is interested in, for instance. We want to make use of the 2 provided test beds that have been introduced to us during the kickoff, as well as possibly a third one that we discussed with our coach briefly. So if it's the possibility to have even a larger area that we can explore, we're all in for that. As I already mentioned, we want to test 2 control modalities. And as metrics, we envisioned map accuracy, number of tracking failures, visual odometry, operator performance, and others which are still to be defined. The risk assessment, we might not have all swarm algorithms in place due to lack of time or people. It's a medium risk. However, we can circumvent it by using traditional methods and relying on the robot operating system, for instance. For connectivity maintenance, we have identified a lower risk, which is that the communications infrastructure, which has been introduced yesterday, might not currently be compatible with our system. But for that, we can find alternative solutions and adapt. For the SLAM-based localization, we might encounter sensor errors due to the extreme environment. So on one hand, we want to mitigate these by having IP67 proof equipment to fight the weather. And on the other hand, we are bringing multiple robotic systems. So if one of them breaks, we have spare parts and we can replace things. The intuitive control modality faces some challenges regarding the environment in which we operate due to lighting. And this can be mitigated by measures that control the lighting. And then we have the terrain limitations and safety issues. So we have limited areas for testing right now. We can, for instance, deploy the rovers across both test beds. Then we would have a bigger area to explore. Or for the hazards on the ridge where robots could be falling down, why not deploy one of those fences that you know from your skiing trip? And in terms of collaboration potential, we talked to P7, 9, and 13. We all would like to have a gigantic swarm collaboration between all teams. And specifically for P7, we exchanged some information towards both of our missions. P9, we introduced them to our swarming language bus. And P13, we were talking about the cognitive workload assessment, as well as the assessment of their of the astronauts or operators in a confined space, and how you can change this with lighting. Yeah, I think that's it, and thank you.
I would like to, first of all, thank teams 3, 4, 5, and 6 for the very fruitful conversations we had yesterday for possible collaborations. I'm not going to reiterate what we discussed because you guys covered that quite beautifully. So just another disclaimer, I'm just going to build upon what my colleague Michael talked about in our first presentation in the interest of time to keep this as short as possible. All right, so without further ado, here are our planned deliverables for the field campaign. We expect to deliver a teleoperated and semi-autonomous rover, plus a solar sintering apparatus that will be mounted on top of it. So these two systems in tandem will be able to produce a sample of a demonstrating sintered structure. So here we have some illustrating images over here. These are sourced from the ESA sponsored project Regolite. So here is a possible demonstrated sintered structure, which may not be what we go for in the field campaign, but that's just an idea of what can be. And here is a stationary solar sintering apparatus, which they have developed, and we are planning to miniaturize in order to be able to carry it around by a rover. So what we need from the IGLUNA management is a means of transporting our rover to the test bed, because even though it would be nice to have a romantic hike with our rover up the Mount Pilatus, we would much rather prefer cable cars or trains to keep the process as painless as possible. Also, as we are using teleoperations, we would like access to the IGLUNA control room so that we can control our rover from far away. We'd also need power outlets to keep all of our devices charged and our batteries fully topped for power, so we can have proper functioning of our entire system. And we need about 4 square meters of storage and workspace so we can do maintenance and keep the rover in a place that will not be in the way of anything when we are not using it. And we also need a relatively flat area of the test bed. The criteria for this area we still do not have defined at the moment, but as soon as we have more information about that, we will definitely let you know on what we need. So the expected results that we want to see at the field campaign is that our rover will be remotely operated with some functions automated. So for instance, our driving would be teleoperated, whereas our sun tracking would be autonomous. Our combined apparatus, the rover and sintering instrumentation, will be capable of sintering sand. So we will probably be providing our own sand to this event, and we will create a few layers of fully sintered material. So at this moment, we are currently working on these two systems independently. So our first rover iteration will likely be completed by the end of October, and our first sintering instrumentation will be completed by the end of, well, actually in a few weeks. So very enthusiastic and exciting on that front. Then we also expect our rover to be able to move to other locations and still be able to sinter. So it'll stop in one place, sinter, and then go to another place and repeat the process. And yeah, we won't be sintering only in one place. Finally, we have some major risks that we have talked about before we entered the IGLUNA competition. So here are just some of the most catastrophic risks that we have pinpointed. First, we felt that maybe the team may fail to meet the milestone deadlines. This will result in a disqualification from IGLUNA, and we mitigate this with a periodic time plan review by the project management. And the result of this would be bottleneck systems will be given extra support and manpower. Another problem would be low solar irradiance on the day of the field campaign. The result of this is that no sintering would be possible. And to mitigate this, we are developing a high power LED screen to substitute solar, a lack of sun. Third problem, a large deviation in relative position between the solar focal beam point and the current layer. This will result in unstable or faultily sintered structure. And to mitigate this, our payload team will conduct repeatability and robustness tests. And any test failures will just result in a redesign earlier in the process. And finally, last but not least, the mechanical failure of the battery is always an impending, a very major disaster that we want to mitigate at all costs. The result would be undesirable combustion. And we expect to mitigate this by embedding it in a robust housing, which will bear all static and dynamic loads associated with normal rover operation. So that's about it. Thank you for your attention.
So hello everybody. We are a PowerHab 2 team from Strathclyde University in Glasgow. At the moment, our team is made up of only 3 members because the academic year is not started yet in Scotland. However, in a couple of weeks, we will be able to include in the team also students from the 4th and 5th year of the Department of Engineering. Yes, our project is focused on power. We chose power because it's a fundamental aspect of our daily life on the Earth, and it is even more important for the feasibility of the human-based habitat on the Moon. For example, in the Moon, we need power to control the temperature, we need power for the lighting system in order to make comfortable or at least survivable the human habitat. We need power for scientific experiments and for many, many other activities in the habitat. Then our mission is to make available this power for the habitat, human-based habitat on the Moon. And our goal for IGLUNA 2021 is to design a system that is able to generate, store, and distribute this power. This is general system overview of our power system. We rely on the sun power, the energy from the sun. We use a system of reflecting satellites to increase the power density that is then collected from a power satellite and beamed down on the ground segment in order to be delivered. Also, to increase the reliability of the system, we consider a solar array farm and a system of energy storage. The overall system is able to distribute continuously during day and night the required energy. So we participated last year in IGLUNA 2020, where we focused on the generation and storing part of the system, doing a preliminary design of the power system. This year, we want to advance the design stage, so going more in the detail and considering the new requirements coming from the new projects. And also, we want to analyze the distribution part of the power system. For the field campaign, we are going to manufacture scale prototypes of some of the components that will be designed in order to present to the general public their physical properties and their advantages for possible moon-based habitat, but also for possible application on the Earth. And we will focus on thermal mass and other systems that were not considered last year, who were not finalized. Also, we will present an interactive software in order to explain our idea behind the software optimization of complex systems. About the risks, besides the uncertainty related to COVID-19, of course, there is a risk about the student composition of the team, because now we don't have students and there is the possibility that some of them will leave the project. However, this risk is quite low because we are in contact already with some of them and they are really motivated. There are many risks related to the technical part of the system. The most important regards the wireless power transmission system, and we know how to mitigate this risk. Other risks related to the system transportation. We spoke with a few of the groups yesterday, and we think that it is very important for us to collaborate with all of them. Indeed, their power requirements is important information for us to start and proceed with our design process. So final, this is an overview of our project, but more details will come in the coming weeks, and then the student team will be defined. And with this, I would like to thank you and leave the floor to the next.
Okay, so this is just to sum up. Our team is a very small team. There is the two of us, I'm Serena and he's Michele, and we are both product designers from Politecnico di Milano. And we are supported by our supervisors that are Annalisa Dominoni and Benedetto Quacquaro, who are were our professors last year, and they are experts in the field of space design because they held the Space for Inspiration course at Politecnico di Milano, which is a course based on designing space objects and stuff like that. So, okay. We want just to sum up the topic of our project. So this year we are working with light. In the previous year, some students, design students from Politecnico have started developing some habitats. And this year we want to improve the atmosphere inside those habitats. How? Through the designing of a lighting system. And in particular, we are presenting at IGLUNA 2 projects with 2 business partners that have already been confirmed. The first one is Gavis and the second one is Minitallux, both Italian companies, but with a very different background. Gavis is much more technical, and with them we are going to present a lighting system, while Minitallux is a bit more focused on design, on the scale of a tangible product, and with them we are going to design something much more tangible and I would say less complex. So the first project, as I was saying before, is based on Gavis, and the lighting system we are going to develop has 2 main goals. The first one is trying to somehow help people that are in space on the basis of circadian rhythm problems. And the other one is doing a system that is able to detect the emotions, but also the other parameters typical of the person in that context that are bioparameters, and change according to their needs. So the idea is that in the past, people had to adapt in space to an hostile environment, while now it's the other way around. So through our project, it will be the habitat itself that tries to help the people that are there. The second one is something less complex. It's with Minitallux, and here we are focusing on the emotional aspect of the project. And in this case, we are doing something that will be shown at the exhibition that people will be able to play with, to touch. So here we are designing a product, a real product. Okay. So going a bit more in detail.
Yeah, now we will explain what we did last semester with the university, and in particular the Space for Inspiration course, which is the course held by Politecnico with the support of ESA. Here you can see some renders that we did, especially for the ISS. So here you can see the ISS with a different way of lighting, something that can really help people, can radically change the environment in order to make it more comfortable, more familiar, something that can help the nostalgic feeling of the astronauts. And as you can see, they are just, they are concepts. They are based on research but they are still concepts. So we didn't go deep in the really technical aspects. We want to reach for Gavis, so for this the first project, something that can be really usable. So also for the field campaign, something that people can go into, interact with it, and try to feel like the astronauts, but at home, so not like they are now. And we want to develop this system that works thanks to some sensor that can feel the bioparameters of the astronauts and understand their feeling, their mood, their emotion, and according to them, make the environment more comfortable, also according to the circadian rhythm. That is something that is essential to work on. While on with Minitalux, we want to create a tangible, a real product, something that can also work on this nostalgia and emotional part, but it's something more tangible. Indeed, if with the games we want to make the lights happen without seeing the source of the light, with this second product, we want to show the source of the light. That must be something more emotional, something that also visitor at the field campaign can touch, can interact with. The preliminary risk assessment that we found out are mainly for the first project, because it's more complex and maybe can create more problem. In particular, on the how we have to understand how to really feel the bioparameters in a really precise way, and to transfer these bioparameters into the in a light output. So this transmission. And at the field campaign, we can have some issues for the visitor, for example, for the privacy. So we have to work also on this one, on this aspect. And for the collaboration, we talked with the group P6 to make the installation inside their lunar habitat. And there is also another possibility, which is the one to put Ray inside Mooney, which is a project that our colleague of Politecnico did for IGLUNA last years. And another one can be with Gavis to provide by them an environment, something that we can do by ourselves. So it's also easier for us to make it here where we are. And another collaboration can be with the P12, which is not physically make the array working with their power, with their energy, but just show, explain, demonstrate that it's feasible. We also talked with group P10 that suggests us something with the sensor and how to really test this project. So thank you, and see you soon.